Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about extensive and normal form games. My name is Rick, and my co-teacher who prepared these notes is Christoph. Okay, so let's have a look at the outline of what we want to cover today. We're going to review several concepts. First being outcomes and utilities. Then we'll discuss solution concepts. And then we'll get into extensive and, for comparison, normal form games. Okay, let's start with outcomes and utilities. So outcomes are just like what they sound like. They describe the various possible results that can happen in a game. Usually they're expressed as the set of utilities that are resulted for each player. We'll use the term outcomes pretty frequently, so you should get used to it and maybe add it to your glossary. As I said, they're often written as the set of strategies played or the resulting payoffs. Utilities are numerical quantities that describe preferences the players have for the various outcomes. Again, utilities is an important keyword, so you should add it to your glossary. Often, well, not just often, always, we can expect utilities to depend on the details of the player. So they can depend on things like money or wealth, risk or risk preferences, the fairness of the situation, the reputation of the player, or even things like how hungry the player is, or other things. It's very common to use money as a simple proxy for utilities. For example, in actual experiments. But we should be a little bit careful when we think about that, because what one player values, how much money they value, might be different than another player's preference for money. For convenience, we will assume that the payoffs we see in the scenarios we write down are the utilities of the players, unless we explicitly say otherwise. Let's look at a simple example. Let's say there are 3 possible outcomes in some scenario, and they are A, B, and C. And let's look at a player alpha. Maybe their utilities for these outcomes are 0, 100, and 200. Clearly then, A is preferred less than B, and B is preferred less than C, so player alpha would prefer outcome C. Let's look at another player, player beta. Maybe their utilities are, let's say, 0, -1, and +1. Maybe pause the video here and make sure you can figure out what the preference ordering is for player beta. Okay, I'll write it down. In this case, B is the worst, so B is preferred less than A, and A is preferred less than C. So again, player beta prefers outcome C. That's all pretty straightforward, right? The only little tricky thing here that you gotta keep in mind is that you cannot conclude that player alpha has a stronger preference for outcome C than player beta. You can't compare utilities across players. All you can do is compare the preferences or the utilities of a single player. And there's even nuances to that we'll talk about later. Okay, let's move on to talking about solution concepts. So the solution concept is at the heart of what game theory is all about. Game theory gives these techniques to solve games. In other words, to predict the likely or credible results or outcomes. Now, in most mathematical kind of oriented courses that you're going to take, you're going to be looking for the single correct solution. But in game theory, it doesn't work like that. There is no single correct solution. And the solution concept are these solution concepts are these techniques that highlight likely outcomes out of all the possibilities. Let me just write down a few examples of various solution concepts. There is the subgame perfect equilibrium. Let's shorten that to SPE. And we saw that when we were talking about the ultimatum game before. There's also the Nash equilibrium. Call that the NE. There's a thing called a Pareto optimum, which we haven't covered, but we will. Let's call it the PO. And there's many more, some of which we'll get into. Lots of fancy words here. Some of them you should commit to memory and or glossary. Solution concepts, subgame perfect equilibrium, Nash equilibrium, and later on we'll talk about the Pareto optimum, so we don't need to worry about that right now. The point here is that once the utilities are known, the solution concepts can be applied systematically. And the details of the game, how we arrived at those outcomes and how we determined those utilities for those outcomes, no longer matter. I see here I wrote, it no longer matters. Let me just scratch that out. That means the application of the solution concept, let's call that the analysis, is solely based on the outcomes or preferences, or maybe I should just say utilities, and not any of the details of the game that got us there. Another consequence of that, which is handy, is that when we're doing exercises, we can just put together trees or matrices with random payoffs. So, for example, we could put together a tree, say this is player 1, this is player 2, and when we look at the outcomes, it could be completely random. So, for example, we could roll dice for all of these 4 outcomes, which would mean we'd have to roll 8 dice. Each of them can take on a value of 1 to 6. So just by doing this, we could create 6 to the power of 8, which is about 2 million games. Not that that really matters, but it's just a demonstration that when we're working with the trees or with our matrices, we can just plug in arbitrary numbers just to make points. And that will let us illustrate the techniques. But keep in mind that the results really have no meaning or broader implications because the context is missing. And that gets at a point that I want to make. Later in this course, you're going to be developing a project of your own, and a key element of the project, and hopefully many discussions in class, will be to provide that context for games. And we're going to do that by carrying out a set of 4 steps. We'll want to grasp a real-world situation that can be represented as a game. By grasp, I mean recognize. Next, we'll want to abstract that scenario into a formal game. That abstraction step will put it into a decision tree or a matrix formalism where you'll have defined the payoffs and presumably the utilities for the players, and then you'll be able to work with it. And that brings us to the third step. That will be to manipulate the game using solution concepts that you've learned in class to arrive at some novel results. And finally, an important step will be to turn that around and explain some implications for that original real-world scenario. So these are the 4 steps that you'll kind of want to keep in mind of what we're trying to achieve here: to grasp, abstract, manipulate, and explain. And of course, I chose those words because they spell game. Isn't that cute? Okay, let's move on to talking about extensive form games, which we also call decision trees. So we analyze extensive form games by using this concept of the solution concept of finding the subgame perfect equilibria. Again, let's shorten that to SPE. And how do we do that? We use a technique called backwards induction. And that means we start at the end and we eliminate all the branches that are based on irrational decisions. So it turns out that the SPE, that the subgame perfect equilibria, is unique, meaning that there's only one of them if no player is indifferent at their decision node. And for example, that can occur if the utilities of all outcomes for each player are different. Think about what that means. What we're saying is that every single player looks at the outcomes and sees a different utility for every single outcome. That's what this phrase in the brackets here, this example is. But can you think of an example where not all the utilities are different for each player, but nevertheless the players are never indifferent at their decision node? If you can, that means that the stuff in the brackets here is not the same as the statement above it. Think about that. If you can find something, bring it to class and show us. For now, we'll just move on. And let's talk about some other ways to analyze or solve, in quotes, games. Let's take a look for comparison let's take a look at normal form games. Sorry about that. Which are also called matrix games. We've talked about the ultimatum game before, so let's look at the ultimatum game as a normal form game. Okay, in a normal form game, we write things as a matrix, as a set of boxes, and we look at the various strategies that the players can employ, and the intersection of those strategies are the possible outcomes. For example, let's say the proposer, which I'll draw in red, has 2 possible strategies. Strategies are high and low. On the other hand, we can look at the responder, which I'll draw in blue, and the responder also has 2 possible strategies that we discussed. They were high only and all. We can construct a matrix from these options, And we can write down the payoffs for each player under these scenarios. Let's start by looking at the responder's payoff. If the proposer plays high in the top left box, the proposer plays high and the responder accepts high only, then the responder gets that high only payoff. So they get H. If the responder accepts everything, accepts all, and the proposer offers high, then again, the responder gets H. Moving down from there, if the proposer offers a low amount and the responder accepts all, then the responder gets that low amount, L. But if the proposer offers a low amount and the responder says, no, I only accept high only, then the responder doesn't get nothing. So in blue here, we've written the payoffs, or presumably the utilities, for the responder. Now we want to write down the payoffs for the proposer. And I'll write those in red. And they're obviously just the remainder if the offer was accepted. So in the top left box, the offer is accepted, so the proposer gets 1 minus H. Top right box, the responder again accepts it, so the proposer gets 1 minus H. In the bottom right box, the proposer offered low and the responder accepted it, so the proposer gets the remainder. And in the bottom left box, the responder rejected the offer, and so nobody gets anything. It's not necessary to offset these payoffs in the boxes. You can just write them beside each other and just put a comma between them. And then you know that the first number is always the row player's payoff. So this and this is for the row player, which in this case is the responder. Wow. No, in this case is the proposer. And the second number written here and here. So the second number in each box is the payoff to the column player. And that's a very standard convention. So the first number is always the row player's payoff, and the second number is the column player's payoff. Let me write column and row, just to be clear about that. Okay, now some things to think about. I'll just state it here and you can think about it for yourself. Every extensive form game can be mapped onto a normal form. But keep in mind that the normal form doesn't explicitly show that the decisions are made sequentially, like we saw in the extensive form of the ultimatum game. And in fact, often in normal form games, players have to decide without knowing their opponent's decision. And that is the definition of a simultaneous game. Simultaneous game you should become familiar with. Let me pose a question for you. In this payoff matrix, you see the responder's choice as a simultaneous choice. Can you think of how you would design a payoff matrix that gives player 2 the freedom to make choices after player 1? And yet the point here is that it would still be written as a payoff matrix, as a normal form matrix game. Think about what the strategies that the responder would have to write down, maybe on a sheet of paper, and submit in order to still respond to what the proposer did. Okay, if you can figure that out, that's awesome. It's not required at this point, and it's a little bit of a puzzle. If you have questions about it, we can try and work through it in class and see if we can figure it out, or after class, or just in discussions. So let's review a concept that we've talked about before, one of our solution concepts. In this ultimatum game, the normal form representation of it, we already know from our discussion of the ultimatum game before that the outcome 1 minus L, or equivalently, we could write that as strategy offer low and accept all, that outcome is a subgame, let me just write, is a subgame perfect equilibrium, SPE. Well, we found that out from the extensive form of the game using backwards induction, but in the matrix form, take a look at the payoff matrix and see if you can infer anything about that. What is so special about this outcome? If anything. You might want to pause here, have a look at the matrix, and see what you can get out of it. And let's get back to it. So what is so special about it? Let's look at the options for the proposer. If they switch their strategy from low to high, then their own payoff or utility drops. It goes from 1 minus L, which is good, to 1 minus H, which is not as good. So the proposer has no incentive to switch. How about the responder? If they switch their strategy, so instead of playing all, they play high only, then again, their payoff drops because they reject the offer. So instead of getting L, they would now get nothing. So again, there's no incentive for this player to switch strategies. And this creates or kind of defines another important solution concept, which we've already mentioned last time when we talked about the ultimatum game. And that is that no player can improve its payoff by unilaterally changing their strategy. And that is the definition of the Nash equilibrium. Again, Nash equilibrium, important concept, keep it in your head. The term unilaterally here, unilaterally, is important. We're going to get back to this, but for now, it just means that only the one player changes their strategy. And that means that players don't have the option to agree on a simultaneous change of strategies. This is what we call non-cooperative game theory, meaning that there's no discussion, or more importantly, no coalition formation among the players. And that's in contrast to cooperative game theory, where this is possible. For now, we're going to focus on non-cooperative games. Okay, there's another couple concepts there. Non-cooperative game theory and cooperative game theory. You should mark those down in your glossary. So returning to the matrix form of the ultimatum game, are there any other observations we can make about it? In particular, are there any other Nash equilibria? So let's draw the payoff matrix again, and we can have a look at it and work through it. So we've got the responder, which again I'll put in blue, and the responder's strategies are to accept high only or to accept all. And then we've got the proposer, and the proposer will make a high offer or a low offer. And these two strategies by the proposer and the two strategies by the responder make something called a 2x2 matrix, and it lays out all the possible outcomes. So let's look at those. Let's start with the responder's payoff again. So in the top left box, if the responder accepts high only and the proposer makes a high offer, then the responder gets that high offer, H. If, on the other hand, the responder will accept anything, accept all, then again, the responder will get H. If the responder accepts all, but the proposer makes a low offer, then the responder gets that low amount, L. And the last case is if the responder only accepts high offers, but the proposer offers a low offer, then nobody gets anything, so the responder gets 0. And looking at the proposer, in 3 of these cases, they just get the complement. And in the final case, where the responder refused the offer, nobody gets anything. So the proposer also gets 0. Okay, now I'm going to draw some things that I call preference arrows. And they indicate the direction of preference. It really only makes sense to do these in these kind of 2x2 matrices where there's just player 1 has 2 choices, player 2 has 2 choices. Because if there's more choices, then it becomes unclear what the arrows mean and where they're pointing to and from. But we can do it here, so let's do it. So to give you an idea what I mean, if I write X arrow Y, that means that Y is preferred. Let me just say Y preferred, I can spell, over X. It's also possible that the players will be indifferent and they won't have a preference. In that case, I'll use a double arrow. You can think of it like a double arrow, kind of like an equal sign. And that means that the players are, well, the one player is indifferent between the choices presented. Okay, so using that, let's look at the preferences for the proposer. On the left-hand side, if the responder is going to accept high only, then the proposer would prefer to make a high offer rather than a low offer, because in the case of a low offer, it's not going to get anything. So the arrow points up, the preference arrow, which means that in this left-hand column, the proposer is drawn towards the upper box. On the other hand, if the responder accepts all, so we're in the right-hand column, then the better option for the proposer is the bottom one, to propose a low offer. And so the proposer prefers the bottom option. Now, for the responder, we can look at the responder's preferences as well. If the proposer makes a low offer, then the responder should prefer all, to accept all. So their preference is to the right. On the other hand, if the proposer makes a high offer, then the responder will get H in either case, regardless of what they choose to do. So they're indifferent to their choices. Okay. So with these preference arrows, you can kind of visualize the Nash equilibrium. They're the kind of the attractors of these arrows. So the bottom right corner, both the arrows point into this box. So this is something we call a strict Nash equilibrium. If we look at the other cases, the bottom left case, you'll see that both the arrows point out of the bottom left box. So it's never, an attractor, and it's not a Nash equilibrium. In the top right box, that's the offer high and accept all scenario. The proposer prefers actually to move away from that. So that's not a Nash equilibrium. The last case is the top left box, where the proposer makes a high offer and the responder will accept high only. In that case, the proposer prefers that outcome, and the responder is indifferent to that outcome. So they don't prefer it over the other one, but they also don't not prefer it. That was a stupid way of saying it. They also don't prefer the other outcome. So that makes this something a little bit more subtle, something called a weak Nash equilibrium. And we'll get into these concepts in more depth later in the lectures and in our exercises. For now, let me just define those terms. We have an SNE, which is a strict Nash equilibrium, and a WNE is a weak Nash equilibrium. They're both Nash equilibria, but they're not quite the same thing. And these terms, we're going to come across them again and again, so add them to your glossary. And let me just rewrite what I've said already. The strategy high and high only, the outcome, high, offer high and accept high only, is another Nash equilibrium, but it's weak because the responder is indifferent to switching. So again, it is a Nash equilibrium because it's not the case that the responder prefers to switch away, but it's weak because the responder also isn't strongly drawn to staying. And why is that important? The solution concept of a weak Nash equilibrium can play an important role, especially in cases, for example, if the responder can somehow convince the proposer that she will accept high only, then we expect the weak Nash equilibrium outcome. Okay, that's all I wanted to cover today, so let's just go over over what we did. So we covered concepts like outcomes, utilities, payoffs, and preferences. We discussed the general idea of solution concepts, and specifically the subgame perfect equilibrium, the Nash equilibrium, and others. Well, we mentioned others. We talked about how to tackle a real problem and how you're going to get into your project and work with it. And as I mentioned, there are 4 steps involved. Those steps are first to grasp the situation, understand that we are dealing with a game. Once you've realized that, then you need to abstract the real scenario into game theoretic formalism. Then you want to manipulate that formalism by applying some solution concepts to get a prediction of what the outcome is going to be in this scenario. And finally, you want to take the results from the solution concept, from your manipulation, and apply it back to explain what's going to happen in the real scenario that you've come up with. And altogether, those 4 steps are GAME. You can probably remember that, right? I had to think really hard about what words I could use to make GAME. I'm still not really happy with all of them, but if you have better words that start with those letters, let me know. Okay, what else did we cover? We covered the extensive form, that is decision trees, and the normal form, that is the matrix form of games. We also talked about sequential versus simultaneous games. We briefly talked about the difference between cooperative versus non-cooperative games. And finally, we started getting into the difference between strict and weak Nash equilibrium. Okay, well, that's all for this lecture. Thanks for watching.